Tonight, something unusual is unfolding across different parts of the world. It does not begin in one place, and it does not follow a single path. Instead, it appears in fragments, separate, distant, and at first unconnected. A storm warning flashes across one region, while in another, rising water begins to swallow streets that only hours earlier were dry. Far to the north, temperatures drop sharply, bringing sudden snowfall where none was expected. And to the west, dry winds move across open land, feeding fires that spread faster than anyone anticipated. Individually, none of these events are unheard of. Storms happen, floods happen, snow falls, fires burn. These are all part of the natural rhythm of the planet. But what makes this moment different is not the events themselves. It is the timing. It is the way they are all happening at once, layered across the same stretch of time, creating a sense that something larger may be at work. Meteorologists begin tracking the situation early. At first, it looks like a standard pattern, one that has appeared before in different forms. But as the hours pass, the data starts to reveal something more complex. A massive atmospheric structure is stretching across a wide region, influencing weather systems in ways that are both predictable and, at the same time, unusually intense. This structure is known as an upper-level trough. It is not something people on the ground can see directly, but its effects are unmistakable. High above the surface, the jet stream dips downward, pulling colder air from the north while allowing warm, moisture-rich air to rise from the south. This interaction creates instability, and instability is where weather begins to change. As the trough deepens, it begins to organize the atmosphere into contrasting zones. On one side, warm air is pulled upward, carrying moisture from the Gulf of Mexico. This air is heavy with energy, invisible but powerful, and as it rises, it cools, condenses, and forms towering storm clouds. These clouds are not passive, they are dynamic systems, constantly building, shifting, and releasing energy in bursts that can become violent. In these regions, storms begin to intensify. Winds pick up, clouds darken, and the atmosphere feels charged. There is a tension in the air that people can sense even before the first drop of rain falls. It is the kind of feeling that makes everything seem slightly off, as if the environment itself is preparing for something. At the same time, in areas just beyond the reach of this warm air, a completely different transformation is taking place. The cold side of the system begins to assert itself. Temperatures drop quickly, sometimes within a matter of hours. What was once mild becomes cold, and what was cold becomes freezing. Moisture in the air turns into snow, falling steadily, covering roads and fields in a quiet but relentless layer. This contrast is one of the defining features of such a system. It is not uniform. It does not behave the same way everywhere. Instead, it creates extremes, placing them side by side in a way that feels almost deliberate. Heat and cold, wet and dry, calm and violent, all existing within the same overarching pattern. Further west, another effect begins to emerge. As the system pulls moisture into certain regions, it leaves others dry. The air becomes lighter, the humidity drops, and winds begin to move more freely across the landscape. These winds are not random, they're guided by pressure differences, accelerated by the very same system that is causing storms elsewhere. In these dry regions, the land becomes vulnerable. Vegetation that has already been stressed by previous conditions now finds itself exposed to fast-moving air and low humidity. It does not take much for a fire to start under these circumstances. Spark, a small ignition, and suddenly, flames begin to move. Once they start, the wind carries them forward, faster than expected, faster than easily controlled. So now, across a wide stretch of land, multiple events are unfolding simultaneously. Storms are building strength. Floodwaters are rising, snow is falling, fires are spreading. Each of these events is driven by the same overarching atmospheric pattern, yet each one manifests differently depending on local conditions. For those observing from a distance, the pattern begins to feel significant. It is not just the presence of these events, but the way they align in time. The human mind looks for meaning in such alignment. It asks questions, searching for connections that go beyond what is immediately visible. Is this normal? Has this happened before? Or is this something new? To answer these questions, scientists look deeper into the mechanics of the atmosphere. They measure energy, movement, and change using a range of tools and concepts. One of the most important of these is something known as convective, available potential energy. This is not something people can feel directly, but it plays a crucial role in determining how powerful a storm can become. When this energy is high, the atmosphere becomes unstable. Warm air rises rapidly, creating strong updrafts that can support the development of severe storms. These updrafts allow clouds to grow taller and more organized, increasing the likelihood of intense weather events. It is not just about whether a storm will form, but how strong it will be when it does. In the regions affected by the warm side of the trough, this energy begins to build. It does not happen instantly. It accumulates over time as heat and moisture combine under the right conditions. Once it reaches a certain threshold, the atmosphere responds. Storms begin to organize more clearly. They move with purpose, guided by winds at higher altitudes. Some produce heavy rainfall, leading to rapid flooding in areas that cannot absorb water quickly enough. Others bring strong winds, capable of causing damage over large areas. In some cases, rotation begins to form within the storm, adding another layer of complexity and risk. Meanwhile, in the colder regions, the snowfall continues. It may seem less dramatic compared to the storms, but it carries its own challenges. Roads become difficult to navigate, visibility drops, and daily life slows down. It is a quieter form of disruption, but no less real. And in the dry regions, the fires continue to spread. Firefighters work to contain them, but the conditions make it difficult. Wind shifts can change the direction of a fire quickly, and the lack of moisture allows it to keep burning. All of this is happening at the same time. Not in sequence, not one after another, but together. It creates a sense of overlap, a layering of events that feels almost synchronized. But even as all of this unfolds on the surface of the planet, something else is beginning to develop far beyond it. High above, beyond the atmosphere, the sun continues its constant activity. Most of the time, this activity goes unnoticed by those on Earth. It is distant, steady, and largely invisible to everyday experience. But occasionally, the sun releases bursts of energy that are powerful enough to be detected across space. At this moment, instruments monitoring solar activity begin to register a change. Spike. A sudden increase in energy output that stands out against the background levels. It is not immediately clear how significant it will be, but it is enough to draw attention. The timing is what makes it stand out. Because while the Earth is already dealing with a complex and intense weather pattern, this new development introduces another layer. Not directly connected, not part of the same system, but occurring at the same time. For those who are watching closely, the question begins to form again. Is this just coincidence, or is there something more to it? The data does not provide an immediate answer. It rarely does. Instead, it presents information, patterns, and possibilities. It requires interpretation, careful analysis, and sometimes patience. Back on the ground, the weather continues to evolve. Storms move across regions, some weakening, others strengthening. Floodwaters rise in some areas and begin to recede in others. Snowfall continues where temperatures remain low. Fires burn where conditions allow. It is a dynamic situation, constantly changing, never static. And above it all, the signals from the sun continue to be monitored. For now, there is no clear connection between what is happening in the sky above and what is happening on the surface below. But the overlap in timing is enough to capture attention. Enough to create a sense that these events, though separate, are part of a larger moment. A moment defined not by a single cause, but by the convergence of many. As night falls in some regions and day begins in others, the pattern remains in motion. It does not stop. It does not pause. It continues, driven by forces that operate on scales both vast and precise. And just as the situation begins to settle into a rhythm, just as it starts to feel like the pattern can be understood, the signals from space grow stronger. Something has been released from the sun, and it is on its way. What began as a series of scattered events is no longer being viewed in isolation. As more data comes in, the pattern becomes harder to ignore. Meteorologists, analysts, and observers across different regions begin to compare notes, timelines, and measurements. The conclusion is not immediate, but it starts to take shape. These are not random occurrences appearing independently. They're being influenced, at least in part, by a shared atmospheric structure that continues to evolve. The same upper-level trough that was first identified is now deepening further. Its reach extends across multiple regions, and its influence is becoming more pronounced. The jet stream, which guides much of the weather in these areas, is bending more sharply, creating stronger contrasts between air masses. Warm air is pushed further north than usual, while cold air drops further south. This interaction does not create balance, it creates tension. In the regions where warm, moist air dominates, the atmosphere feels heavy. The air carries a thickness that is not always visible but can be sensed. It is the kind of air that builds slowly, trapping heat during the day and refusing to release it easily at night. This trapped energy does not remain still. It accumulates, layer by layer, feeding into a system that is becoming increasingly unstable. This instability is measured using convective available potential energy, and the values being recorded begin to rise. Not in small increments, but in noticeable jumps that signal a change in the atmosphere's behavior. High levels of this energy mean that when air begins to rise, it does so with force. Updrafts become stronger, clouds grow taller, and storms gain the ability to sustain themselves longer than usual. Storm systems begin to organize with greater clarity. They no longer appear as isolated clusters of clouds. Instead, they form lines and structures that move with direction and speed. Some stretch across entire regions, bringing consistent rainfall that does not let up. Others become more concentrated, producing bursts of intense weather that can change conditions in minutes. Rainfall begins to accumulate in ways that exceed expectations. In areas where the ground is already saturated, additional water has nowhere to go. It begins to pool, then to flow, and eventually to overwhelm drainage systems that were not designed to handle such volume in such a short period of time. Streets turn into channels, and low-lying areas begin to fill. At the same time, the cold side of the system continues to push downward. Temperatures drop further, reinforcing the conditions needed for snowfall. The boundary between rain and snow becomes more defined in some places and more chaotic in others. A slight shift in temperature can change precipitation from one form to another, creating a mix that complicates travel and daily activity. Snowfall intensifies in certain regions, not because of a single burst, but because of sustained conditions that allow it to continue over extended periods. It accumulates steadily, adding weight to structures, covering infrastructure and slowing movement. The impact is gradual but persistent, building over time rather than arriving all at once. Meanwhile, in the drier regions, the effects of the system are becoming more severe in a different way. The same atmospheric dynamics that are pulling moisture into some areas are drawing it away from others. The air becomes increasingly dry, and humidity levels drop to the point where even small sources of heat can become significant. Winds begin to accelerate as pressure differences increase. These winds are not constant in direction or speed, shift, sometimes subtly, sometimes abruptly, making conditions unpredictable. For those dealing with active fires, this unpredictability adds another layer of difficulty. A fire that seemed manageable can change direction without warning, spreading into new areas before containment measures can adjust. Fire behavior under these conditions is not linear. It does not spread evenly. It moves in patterns shaped by terrain, wind, and available fuel. Dry vegetation becomes a pathway, and once ignited, it allows flames to travel quickly. The heat generated by the fire can create its own local conditions, drawing in air and intensifying its own movement. Across all of these regions, the sense of escalation continues to grow. It is not just that conditions are active, it is that they are intensifying at the same time. Each system feeds into the overall perception that something larger is unfolding, something that extends beyond individual events. Observers begin to look back at historical data, searching for similar patterns. They find examples of strong troughs, of widespread storms, of simultaneous weather events. None of this is entirely new. The combination, the timing, and the scale create a situation that feels different. As this analysis continues, attention begins to shift upward again. The signals from solar monitoring stations have not diminished. Instead, they have become clearer. The initial spike that was detected earlier is now being identified more precisely. It is classified as an X-class solar flare, one of the most powerful categories of solar activity. Such flares are capable of releasing enormous amounts of energy in a short period of time. This energy travels outward, not as a single wave, but as a complex burst that can include radiation and charged particles. The immediate effects are felt in space. But depending on the direction and strength of the event, there can be consequences closer to Earth. Accompanying this flare is something even more substantial. A massive ejection of solar material has been observed leaving the surface of the Sun. This phenomenon, known as a coronal mass ejection, involves billions of tons of plasma being propelled into space at high speed. The trajectory of this ejection is critical. Not all such events are directed toward Earth. Many pass by without significant interaction. But in this case, early observations suggest that at least part of the ejected material is moving along a path that could intersect with Earth's magnetic field. This possibility introduces a new element into the overall situation. It does not directly affect the weather systems already in motion, but it adds another layer of activity occurring within the same time frame. If the ejection reaches Earth, it could interact with the planet's magnetic field, potentially leading to a geomagnetic storm. Such storms can have effects on satellites, communication systems, and navigation technologies. They can disrupt signals, create fluctuations in power systems, and produce visible phenomena such as auroras at lower latitudes than usual. These effects are well documented and understood within the context of space weather. But when viewed alongside the ongoing weather events on Earth, the timing creates a powerful impression. This feeling is not limited to experts. It extends to the general public, to those experiencing the effects directly, and to those observing from a distance. The overlap of events becomes a point of discussion, a source of speculation, and in some cases, concern. Questions begin to surface more frequently. Are these events connected? Is there an underlying cause that links them together? Or is this simply a rare alignment of independent systems? The answers are not immediately obvious to those without access to detailed data and analysis. Back on the ground, the weather continues its progression. Storm systems move forward, leaving behind areas of damage and disruption. New systems form behind them, following the same pathways shaped by the larger atmospheric structure. Floodwaters reach their peak in some regions and begin to recede in others, leaving behind the effects of their passage. Snow continues to fall where temperatures remain low, adding to accumulations that must eventually be managed. In the drier regions, firefighting efforts continue, adapting to changing conditions as best as possible. Each area deals with its own challenges, yet all are part of the same broader moment. Above, the solar event continues its journey. Instruments track its movement, updating projections and refining estimates of its potential impact. The distance between the Sun and Earth is vast, but at the speeds involved, it does not take long for solar material to travel that space. As the projected arrival time approaches, attention increases. Not because of fear, but because of the need to understand and prepare. Space weather, like atmospheric weather, is a field that relies on observation, prediction, and response. And so, the situation continues to unfold on two levels. On the surface of the planet, weather systems driven by atmospheric dynamics create a range of impacts that vary by region. Above the planet, solar activity introduces the possibility of additional effects, separate in cause, but overlapping in time. The pattern holds, the intensity remains, and the sense that something significant is happening does not fade, grows, shaped not just by the events themselves, but by the way they are experienced together. As more information becomes available, the picture becomes clearer in some ways and more complex in others. There is no single explanation that ties everything together, no simple narrative that can account for every detail. Instead, there is a convergence of systems, each operating according to its own rules, yet intersecting in time. And as this convergence continues, one thing becomes certain. The situation has not yet reached its peak. Inactivity is no longer just a signal, but a confirmed event, with measurable structure and direction. The energy release that was first detected has now been classified clearly as an X-class solar flare. This classification is not based on appearance, but on intensity. It represents one of the strongest types of solar flares that can occur, capable of releasing vast amounts of energy in a short period of time. The flare itself is a burst of radiation traveling outward at the speed of light, reaching Earth in minutes. This initial radiation can affect the upper atmosphere, particularly the ionosphere, where radio signals travel and reflect. But the flare is only part of the event. Following it, and often associated with it, is something much larger and more substantial. Observations confirm the release of a massive cloud of solar plasma, known as a coronal mass ejection. This is not a burst of light, but a physical ejection of charged particles, billions of tons of matter propelled outward into space at extremely high speeds. The movement of this ejection is not random. It follows magnetic field lines that extend from the sun into the surrounding space. These magnetic structures can guide the plasma in different directions, and only a fraction of such events are directed toward Earth. In this case, analysis indicates that at least a portion of the ejected material is aligned with a path that intersects the Earth's orbit. This alignment is what transforms the event from distant solar activity into something with potential consequences closer to home. The distance between the Sun and Earth is immense, but the speed of the ejected material reduces the travel time to a matter of hours to days, depending on the velocity of the particles. Instruments track this movement continuously, refining estimates as new data becomes available. As the cloud of charged particles travels through space, it carries with it its own magnetic field. When it reaches Earth, it does not simply pass by unnoticed. It encounters the Earth's magnetic field, a protective barrier that surrounds the planet and deflects much of the solar wind under normal conditions. But during a strong event, this interaction becomes more intense. If the orientation of the incoming magnetic field aligns in a certain way with Earth's magnetic field, it can allow energy to transfer more efficiently into the system. This process can lead to disturbances known as a geomagnetic storm. These storms are not visible in the same way as atmospheric storms, but their effects can be significant in the systems that rely on stable electromagnetic conditions. Satellites orbiting the Earth can experience increased drag as the upper atmosphere heats and expands. Communication systems that depend on radio waves can encounter interference, particularly at certain frequencies. Navigation systems, including those used for positioning and timing, can become less accurate as signals are disrupted or delayed. These effects are well understood within the field of space weather. They have been observed before, studied extensively, and modeled to improve prediction and response. What makes this moment stand out is not the presence of a solar event, but its timing in relation to everything else that is happening. On the surface of the Earth, the atmospheric system continues to produce a range of intense conditions. Storms driven by the upper-level trough remain active, with some regions experiencing repeated waves of severe weather. The energy within the atmosphere, measured through convective available potential energy, remains elevated in key areas, supporting the continued development of strong storms. Rainfall persists in regions where moisture continues to flow from the Gulf of Mexico, feeding systems that move slowly or stall, increasing the risk of flooding. In colder regions, snowfall remains steady, adding to accumulations that have already begun to impact daily life. In dry regions, winds continue to drive fire behavior, creating challenges for containment efforts. Each of these systems operates independently, driven by local conditions and the broader atmospheric pattern. Yet when viewed together, alongside the developing solar event, they create a layered picture that feels interconnected. Observers begin to describe the situation in broader terms. It is no longer just a weather event or a solar event. It is a moment where multiple systems, each complex in its own right, are active at the same time. This overlap draws attention not because it is impossible, but because it is uncommon enough to stand out. As the solar particles continue their journey, monitoring systems provide updated projections. The estimated arrival window narrows, and preparations begin in sectors that could be affected. Satellite operators adjust orbits and operational modes to reduce risk. Communication networks review protocols for potential disruptions. Power grid operators monitor conditions that could lead to fluctuations. These actions are precautionary, based on experience and planning rather than immediate impact. They reflect an understanding that while such events are manageable, they require awareness and readiness. Back on the ground, the weather systems begin to show signs of evolution. Some storms weaken as they move into less favorable conditions. Others intensify briefly before dissipating. The pattern remains active, but it shifts, as all weather systems do, responding to changes in temperature, pressure, and available energy. Flooded areas begin to assess damage as waters stabilize or recede. Snow-covered regions manage the effects of accumulation, clearing pathways and restoring movement. Fire-affected areas continue to respond to changing conditions, adjusting strategies as winds shift and humidity levels fluctuate. The situation remains dynamic, but there is a sense that it is being understood more clearly. Data continues to come in, models are updated, and forecasts are refined. Each piece of information adds to the overall picture, reducing uncertainty even as the systems themselves continue to change. Above, the solar event approaches its point of interaction. The leading edge of the ejected material begins to reach the outer boundaries of Earth's magnetic influence. Instruments detect changes in the solar wind, increases in particle density, and shifts in magnetic orientation. These signals indicate that the interaction is beginning. As the charged particles encounter the magnetic field, energy is transferred into the system. The magnetosphere responds, compressing on the side facing the sun and stretching on the opposite side. Currents are induced, and energy begins to flow along magnetic field lines toward the polar regions. One of the most visible effects of this process is the enhancement of auroral activity. Lights that are usually confined to higher latitudes begin to appear further south or north than usual, depending on the hemisphere. These lights are a direct result of particles entering the upper atmosphere and interacting with gases, producing emissions that can be seen from the ground. While visually striking, the auroras are only one aspect of the interaction. At higher altitudes, satellites experience changes in their environment. Increased radiation levels and atmospheric expansion can affect their operation and trajectory. Systems designed to handle such conditions activate protective measures, adjusting operations to maintain stability. Communication systems may begin to show signs of disturbance. Signals that rely on the ionosphere can become less reliable as its structure changes under the influence of incoming energy. Navigation systems may experience slight deviations, requiring correction and monitoring. These effects vary in intensity depending on the strength of the incoming event and the orientation of its magnetic field. Not all geomagnetic storms produce significant disruption, but each one is studied carefully to improve understanding and response. As all of this unfolds, the perception of connection between the solar event and the weather systems on Earth becomes more pronounced in the minds of observers. The timing is too close, the overlap too clear to ignore entirely, even if the mechanisms are different. Questions continue to circulate not just among the public, but also in discussions that seek to clarify the nature of what is being observed. The need to distinguish between correlation and causation becomes more important as the narrative develops. From a scientific perspective, the distinction remains clear. The atmospheric conditions are driven by processes within the Earth's system, influenced by temperature gradients, moisture availability, and dynamic air movement. The solar event is driven by magnetic activity on the sun, operating on a completely different scale and through different mechanisms. There is no direct pathway through which the solar event influences the formation of storms, the occurrence of floods, or the spread of fires. The systems are separate, even as their timelines overlap. Yet the experience of witnessing both at once creates a powerful impression. It highlights the complexity of the environment in which these systems operate, a complexity that spans from the surface of the Earth to the space that surrounds it. As the geomagnetic activity continues, monitoring systems track its progression. The intensity is measured, categorized, and compared to previous events. Early indications suggest that while the storm is significant, it remains within the range of what has been observed before. This provides a level of reassurance, but it does not diminish the importance of the event. Each occurrence adds to the body of knowledge, improving the ability to predict and respond in the future. Below, the weather systems begin to show signs of gradual transition. The trough that has been driving much of the activity starts to shift, its influence changing as it moves and weakens. Conditions begin to stabilize in some regions, even as they remain active in others. The peak of the combined moment approaches, defined not by a single event, but by the convergence of many. Storms, floods, snow, fire, and solar activity all reaching points of intensity within a similar time frame. It is a moment that captures attention not because it breaks the rules of nature, but because it demonstrates them so clearly. Multiple systems, each following its own path, intersecting in time to create an experience that feels larger than any one of them alone. And as the solar particles continue to interact with the Earth's magnetic field, and the weather systems continue their gradual evolution, one thing becomes increasingly evident. The sense of connection is powerful. But the truth behind it is more complex than it first appears. By now, the intensity of everything that has unfolded begins to settle into a clearer picture. Not because the events themselves have stopped, but because the data surrounding them has become more complete. Patterns that once appeared uncertain are now understood with greater precision. The overlap that once felt mysterious begins to separate into distinct layers, each governed by its own rules, each following its own path. The same atmospheric system that shaped the earlier stages continues to weaken and shift. The upper-level trough that once stretched deeply across regions is no longer as pronounced. It begins to lift, its influence gradually diminishing as the jet stream straightens and the contrasts between air masses become less extreme. This transition does not happen instantly. It unfolds over time, reducing the intensity of conditions rather than eliminating them all at once. Storm systems that once drew strength from high levels of convective available potential energy begin to lose that energy. The atmosphere stabilizes in stages, making it harder for strong updrafts to form. Clouds that once grew rapidly now struggle to reach the same heights. Rainfall continues in some areas, but it becomes more moderate, more consistent with typical patterns rather than extreme bursts. Flooded regions begin the slow process of recovery. Water levels stabilize, then gradually recede. What remains is the impact left behind, the evidence of how quickly conditions changed. How roads, structures, and systems designed for normal conditions reveal their limits under stress. The focus shifts from response to assessment, from immediate action to understanding what happened and why. In colder regions, snowfall decreases as temperatures begin to rise slightly. The boundary between freezing and above freezing conditions shifts, turning snow into slush and eventually into runoff. This transition introduces its own challenges, as melting snow adds to existing water levels, contributing to delayed flooding in areas that had not previously been affected. In the drier regions, the winds begin to ease. The same forces that once accelerated air movement weaken as pressure differences reduce. Fire behavior changes accordingly. Flames that once spread rapidly begin to slow, giving firefighting efforts a better chance to contain them. The risk does not disappear, but it becomes more manageable. Across all of these regions, there is a gradual return toward balance. It's not a complete reset, but a movement away from extremes. The atmosphere, which had been pushed into a state of heightened activity, begins to release that tension. At the same time, above the planet, the solar event reaches its later stages. The geomagnetic storm triggered by the earlier coronal mass ejection begins to subside. The interaction between the incoming particles and Earth's magnetic field weakens as the bulk of the ejected material passes by or disperses. The magnetic field, which had been disturbed, begins to return to a more stable configuration. Currents that were intensified during the peak of the storm decrease, and the systems affected by those changes begin to normalize. Satellites resume standard operations, communication signals stabilize, and navigation systems regain their typical accuracy. Auroral activity, which had extended into unusual regions, retreats back toward higher latitudes. The visual display fades, leaving behind only the data that was collected during its peak. For those who witnessed it, the memory remains as a rare and striking experience. With both the atmospheric and solar systems moving toward less intense states, the broader picture becomes easier to analyze. What once appeared as a single, overwhelming moment now reveals itself as a convergence of independent processes. This is where the distinction becomes critical. The weather systems on Earth were driven by atmospheric dynamics. Temperature differences, moisture transport from the Gulf of Mexico, and the structure of the jet stream created the conditions for storms, flooding, snow, and fire. These processes operate within the Earth's environment governed by physical laws that have been studied extensively. The solar event, on the other hand, originated from magnetic activity on the Sun. The X-class solar flare and the associated ejection of plasma were the result of energy stored and released in the Sun's magnetic field.
Oh.
These processes occur far from Earth and follow a different set of physical principles. There is no direct mechanism that links these two systems in a way that would cause one to influence the other. The solar activity does not trigger atmospheric storms, and atmospheric conditions do not affect solar flares. They exist in separate domains, connected only by the fact that Earth is located within the Sun's broader environment. What created the impression of connection was timing. Multiple systems reached points of intensity within the same period. This overlap is what gave rise to the sense that something larger, something unified, might be occurring. But when examined closely, the events separate into their individual causes. This type of situation is described as a compound event. It refers to the occurrence of multiple independent phenomena at the same time. Each event has its own origin, its own development, and its own impact. But when they coincide, their combined effect can be more significant than any single event alone. The importance of understanding this distinction goes beyond explanation. It affects how responses are planned, how resources are allocated, and how future events are interpreted. Treating independent systems as a single connected event can lead to misunderstandings, while recognizing their independence allows for more accurate assessment and preparation. At the same time, the perception of connection is not without consequence. The human tendency to look for patterns plays a role in how events are experienced. When multiple intense situations occur together, it creates a narrative that feels cohesive, even if the underlying causes are not. This narrative can influence behavior, decision-making, and communication. It can shape how information is shared and how it is received. In some cases, it can lead to speculation that goes beyond what the data supports. In others, it can simply reflect the natural response to complexity. From a scientific perspective, the goal is to clarify without dismissing the experience. The events were real. Their impacts were significant. The overlap was notable. But the explanation lies in the interaction of separate systems rather than a single hidden cause. As the data from both the atmospheric and solar events is analyzed further, patterns emerge that reinforce this understanding. The timing, while close, falls within ranges that have been observed before. The intensity of each event, while notable, remains within expected limits based on historical records. This does not make the moment insignificant. It highlights the capacity of natural systems to produce multiple challenges at once. It demonstrates how different parts of the environment can become active simultaneously, creating situations that require coordinated response. Emergency services, for example, faced demands from multiple directions. Flood response teams, fire management units, and storm recovery efforts all operated within the same time frame. This overlap required adjustments in how resources were deployed and how priorities were set. Communication systems, while largely stable, had to account for potential disruptions from the geomagnetic activity. Monitoring and contingency planning ensured that any issues could be addressed quickly, minimizing impact. Communities experienced the events directly, dealing with conditions that changed rapidly and required adaptation. Whether it was preparing for storms, managing flood risks, clearing snow, or responding to fire threats, the challenges were varied but interconnected through timing. As the situation moves further away from its peak, the focus shifts toward understanding and learning. Data collected during this period becomes part of a larger data set used to improve models and predictions. Each event contributes to a more detailed picture of how systems behave under different conditions. The atmospheric data helps refine forecasts for future weather patterns, improving the ability to anticipate similar situations. The solar data adds to the understanding of space weather, enhancing prediction models for geomagnetic storms and their potential effects. Together, these insights strengthen the ability to respond to future events, even when they occur simultaneously. The goal is not to prevent such occurrences, which are part of natural processes, but to manage their impact more effectively. As clarity replaces uncertainty, the sense of mystery begins to fade. The environment in which these systems operate is not simple or linear. It is layered, dynamic, and capable of producing multiple outcomes at once. The events that unfolded were not a sign of something beyond understanding. They were an example of how different systems can align in time without being causally linked. They demonstrated the importance of observation, analysis, and clear interpretation. And as the final effects of both the weather systems and the solar activity continue to diminish, the moment transitions from active event to recorded history, not as a single story, but as a collection of events that, together, created a powerful impression. An impression shaped by coincidence, complexity, and the natural behavior of systems operating on different scales. The connection that seemed so strong at first was not in the cause. It was in the experience. As the intensity fades and the immediate urgency gives way to reflection, what remains is not confusion, but clarity shaped by everything that has been observed. The storms that once dominated entire regions begin to lose their structure, breaking apart into smaller systems that no longer carry the same force. The floodwaters that rose quickly now recede slowly, leaving behind quiet evidence of how high they once reached. Snow that fell steadily begins to melt, and the fires that spread under dry winds are brought under control as conditions shift. The movement does not stop, but it changes direction, easing away from extremes and returning toward balance. Above the planet, the disturbance caused by the solar event continues to weaken. The geomagnetic storm that followed the earlier coronal mass ejection loses intensity as the stream of charged particles disperses. The magnetic field stabilizes, currents settle, and the systems that briefly adjusted to those changes return to normal operation. Satellites resume standard functions, communication networks regain consistency, and navigation systems correct any temporary deviation. The moment that once felt crowded with overlapping events begins to stretch out in memory, revealing the sequence within the simultaneity. What seemed like a single unfolding situation separates into its individual components, each with a beginning, a peak, and a decline. The timing that once made everything feel connected now becomes something that can be measured, compared, and understood. Looking back, the atmospheric system that drove much of the activity followed a path that can be traced with precision. The upper-level trough developed, deepened, and then gradually weakened, shaping the movement of air masses across wide areas. Warm, moisture-rich air drawn from the Gulf of Mexico fed storm development, while colder air reinforced snowfall in other regions. The imbalance between these air masses created the conditions necessary for instability, and that instability, measured through convective available potential energy, determined how intense the resulting weather would become. None of this occurred outside the expectations of atmospheric science. The variables were known, the processes understood, and the outcomes, while sometimes severe, remained within the range of what has been observed before. The difference was not in the mechanisms, but in the alignment of their timing. At the same time, the solar activity followed its own course, driven by forces that operate far beyond the Earth's atmosphere. The X-class solar flare released energy that traveled outward, accompanied by the massive ejection of plasma that eventually interacted with Earth's magnetic field. This interaction produced effects that were measurable and, in some cases, visible. But it did not extend into the processes that govern weather on the surface of the planet. These two systems, atmospheric and solar, existed side by side in time, but remained separate in cause. Their overlap created a moment that felt unified, but their independence defined the reality of what occurred. Understanding this distinction is what brings the final clarity. It is not enough to observe events as they happen. It is necessary to understand how and why they happen, to separate coincidence from causation, and to recognize when patterns are real and when they are perceived. The concept of a compound event becomes central in this understanding. Multiple independent processes can occur simultaneously, each contributing to the overall experience without directly influencing one another. This does not reduce the significance of the moment. In many ways, it increases it because it shows how different systems can converge in time to create complex situations that require careful response. The impact of such convergence is not theoretical. It is practical, affecting how systems function and how people respond. Emergency services that would normally handle one type of event at a time must adapt to multiple demands. Infrastructure designed with specific conditions in mind must handle variations that exceed those expectations. Communities must respond to changing conditions that do not follow a single pattern. These challenges highlight the importance of preparation, flexibility, and coordination. They show that resilience is not just about responding to individual events, but about managing the overlap between them. When multiple systems become active at once, the ability to adapt becomes as important as the ability to predict. At the same time, the human response to such moments reveals something equally important. The search for patterns, the instinct to connect events, and the tendency to look for a single explanation are all natural. They are part of how people make sense of complexity. But they can also lead to conclusions that do not align with the underlying reality. Recognizing this does not diminish the experience. It refines it. It allows for a deeper understanding that goes beyond initial impressions, replacing uncertainty with knowledge and speculation with clarity. As the data from this period is compiled and analyzed, it becomes part of a larger framework used to improve future responses. Meteorological models are updated with new information, refining their ability to simulate similar patterns. Space weather monitoring systems incorporate the observations to enhance prediction accuracy for solar events and their potential effects. Each piece of information adds to a growing body of knowledge that supports better decision-making. It does not prevent such events from occurring, but it improves the ability to understand them, to anticipate their impact, and to respond effectively. In the end, what stands out is not a single event or a single cause, but the interaction of multiple systems operating within their own domains. The atmosphere responded to imbalances in temperature and moisture. The sun released energy through magnetic processes. The Earth's magnetic field reacted to incoming particles. Each system performed according to its nature, without coordination, without awareness of the others. Yet for those observing from within this environment, the experience felt unified. It felt like a single moment of change, a point where different forces came together to create something larger than expected. That feeling is real, but it is shaped by perception as much as by reality. The reality is more complex, but also more grounded. It shows a world where systems operate independently, yet overlap in time, where patterns emerge not from hidden connections, but from the natural behavior of complex processes. As normal conditions continue to return, the sense of urgency fades, replaced by reflection. The events become part of memory, part of record, part of the ongoing effort to understand the environment in which they occurred. There's no single conclusion that simplifies everything into one idea. Instead, there's a recognition that complexity does not always require simplification. Sometimes it requires acceptance that multiple things can happen at once, for different reasons, without being directly linked. That understanding does not reduce the importance of what happened. It enhances it, because it shows how much is always in motion, how many systems are constantly active, and how their interactions in time can shape experiences that feel extraordinary. The moment that once seemed uncertain now stands as an example of how clarity can emerge from observation and analysis. It demonstrates that even when events appear connected, the truth can lie in their independence. And as everything continues to move forward, as new patterns form and old ones fade, the lesson remains. Not everything that happens at the same time is connected, but everything that happens still matters.